Hello, I'm Eric Windish with Cloud Scaling, and today I'm speaking about distributed RPC in OpenStack Nova with ZeroMQ. This is a driver which has been developed against Nova Essex and is being tracked for inclusion into the fulsome release upstream. Again, it's available currently as a plugin for Essex, and this has an Etherpad, or had an Etherpad, with the OpenStack Design Summit. My handle on Twitter is ewindish. I'm currently with Cloud Scaling, and I've been building cloud infrastructure since 2006 and hosting infrastructure since 2002, 2003. So we were seeking to solve a problem in the messaging bus and RPC mechanism within OpenStack, where OpenStack has been using, or Nova has been using, a message queue broker, which is generally RabbitMQ, or historically RabbitMQ. An earlier cloud scaling engineer, Zed Shaw, implemented a abstraction layer to implement pluggable implementations for the RPC mechanism, and there's currently besides Rabbit, a Cupid driver has been introduced as of Essex, and obviously this is we're going to be introducing the ZeroMQ driver in this talk. So here we see a brokered messaging pattern where an application speaks to the API, to the Nova service. All the Nova components, the API, the Nova network, Nova scheduler, Nova compute, speak through the message broker. And the message broker here is a single point of failure. I'm sorry, this slide actually is that the Nova scheduler can actually fail, right? It's an edge node. The message broker continues running, of course, if you lose an edge node. But if you have a message queue in the middle and the message queue itself fails, let's say you have RabbitMQ and RabbitMQ fails, then you lose all of your messaging. It's not just queuing, it's your entire messaging platform. You can implement HA failover for so-called high availability. And in this, instead of having a single point of failure in your message queue, I believe that you're implementing a new single point of failure, which is your failover service daemon. You have to implement this HA failover service daemon, which can fall over itself. And one of the problems with this is that you don't know if it's going to work until you actually fail one of those message queues to see if the second message queue takes over. And then you have to automate the testing and automate intentional failures and test those failure scenarios to make sure that it works. It's not a baked-in feature, and the problem is that HA failover fails. So there's a way you can fix this with RabbitMQ or Cupid AMQP services, and this is to go to a decentralized model. And many of the RabbitMQ guys are actually recommending a pattern such as this, where you can decentralize and send to multiple message queues, and those message queues can send to arbitrary hosts. And the problem with with decentralized patterns, these are nuclear reactor sites throughout Asia, and this is a decentralized pattern. The idea is that you can lose any one, probably more than one of these nodes, and you will still have power throughout Asia. You're not going to lose power, worldwide by losing one or even two nodes. But when a power plant melts down, it's really, really bad for the guys that are at that data center or at that site, right? And when something like, say, RabbitMQ falls over, it's not pretty. So with the decentralized model, it's definitely a lot prettier than with a direct failover method or a single broker. Your message queue fails, and the messages go to a different message queue, and then they get routed to the machines that they belong to. You can and or will have abandoned and lost messages here. If you use durable messages, then that second message queue may come up and may not come up, and it may send those messages out for you. Whether or not you wanted to do that is kind of debatable, depending on message expirations, and there's actually some work to be done in Nova on improving message expirations. So you lose those messages, and it's not perfect. It's certainly would be an improvement over what's in Nova currently, but we believe that the real solution to this is the ZeroMQ distributed RPC. And with this, we implement a peer-to-peer pattern. So an application speaks again to something, say the Nova API, and all the components such as the API, Nova Network Scheduler, Compute, all speak directly to each other. There's no man in the middle. There's no middleware precisely to fall over and to break. There's no HA failover scenario that has to be implemented. And if we lose an edge node, we lose an edge node. It's actually the same as in Rabbit, except in one of the earlier slides where you lose an edge node, you just do, except your messaging bus itself remains active. And if you were to say run 2 Nova schedulers, they horizontally scale, and if you lose one, you don't lose scheduling, you just lose that particular scheduler. And again, the messaging bus itself is not failing, so it's very robust. So you can, to send a message to a remote machine, you send an RPC cast as an example, and we're sending this to topic.host in the upper left corner. And a publisher, an API, opens a push socket into a pull socket of the worker. And push and pull are ZeroMQ parlance, which are ZeroMQ socket types. We're saying that this socket only can push messages and this other socket can only pull messages. And this is essentially how we send a message. That's an RPC call, or an RPC request. And this is a reply, and it looks identical. So to clarify, an RPC cast does not care for a response. It only executes a method on a remote machine. No reply is expected, no reply is received. If you want to implement replies, then you use a call method, or you use callback. You use callbacks in an actor model or so forth. So this is so if you want to send a call message, which all the messaging is done asynchronously through the previously demonstrated cast messaging. If you want to do a call method, which on the client side blocks, then we actually implement that through the asynchronous cast messages and do all the callback method, the callbacks for you transparently within the driver. So this is the code for the send method. I've stripped out some of the arguments. What it does, it takes the original payload, which is the original method call, and it wraps it it essentially decorates it with a reply method, dash reply, and or hyphen reply, and hyphen. The hyphen actually is used internally by the ZeroMQ driver to indicate that this goes not to a standard service module within Nova, but actually stays within the driver in what we call the internal context, which is, again, it's parlance of Nova. It's possible that where we have RPC context, we could change it to internal context, or we can modify internal context. And we essentially did not change it just because we knew that we could create a new context and trust that it was going to work and it was going to be stable. And we didn't know, it wasn't certain if we can modify RPC context safely. So we erred on the side of caution until we could get some further feedback from the community and some of the core developers on that. And so far the feedback on how we've done it has been positive, and we can evaluate that later if we want to do it differently, especially as we merge more of this code into common. So we decorate everything into this reply method, and then the arguments are the original call, and we indicate the return path for the response. Then we register a message waiter, which waits for the reply, and we send a cast to that host, which is sending the actual message that was on the previous slide, and then we receive the messages from that remote machine, the replies. We unpickle them and have our response. First of all, pickle was not the first choice. It just happened to be something that worked, and there were other serialization methods. There are other serialization protocols which we tried and preferred to use and did not work, and we are currently discussing with some of the Nova core developers on and making sure that we can we're kind of aligning to make sure that we're not passing things like, say, objects through the RPC mechanism, and standardizing on that so that we can use JSON serialization as an example. Also, in this slide, you can see that there is a general timeout, and there's also a timeout for the response, and there's also a timeout for the original cast. And some communication with the community is that we want to make this variable, and this timeout, this 30-second timeout, currently does not exist within Rabbit, and actually is a bug that it doesn't exist with Rabbit, and it should, or rather with the Rabbit driver. So this is going to be we're going to implement this as change this 30-second hard-coded value to a configuration variable, and this is also going to be implemented within the Rabbit and Kombu driver, Rabbit, Kombu driver, and the Cupid driver where it doesn't currently exist. This is the reply method. This actually implements the dash reply. We execute the originally requested call. We get a response for that, and then we send that response back to the originally calling host. The original calling host, we were actually wrapping that response into a method called process reply. And this is essentially the process reply method, and this just joins to the message waiter, which we were using in an earlier from the original call method. So this just joins, this demonstrates the flow of an actual call method. This is visualization of the code that we just reviewed. So in Nova, there is a problem of bare topics. There are two different types of topics. Scheduler.host 1, and in this case, we know that we send messages to host 1. It's kind of straightforward. We can split the string and we can say send it to host 1. But we don't necessarily know where messages for scheduler go. And these are queue names. Like say if this was RabbitMQ, these would be queue names. So you have a queue called scheduler, and machines will be listening on this scheduler queue, and you'd have multiple schedules. They'd be listening on that queue, and they each pull one off, round robin like. And you would also have, say, a queue for scheduler.host1, and there would be only one host actually listening, pulling messages off that queue, and that would actually be host 1. With ZeroMQ, we can send messages directly to host 1, and we can be fairly intelligent about that based simply on this name. But messages for a general queue such as scheduler is less obvious. So what we've designed is matchmaking. There's a matchmaker module, and that really comes down to being a rewrite engine. Every incoming topic is mapped to an array of topics and hosts, and usually returns a single topic host. When it returns more than a single topic host is usually for fan-out messages, where we say that we want to execute a fan-out call where we send a message to every machine. Say we want to send a message to every scheduler. So if you want to send a message to every scheduler, then the matchmaker would presumably return a list of every scheduler that it is aware of. So in the Essex code, this is very rudimentary and very ZeroMQ specific, and in Folsom we're looking at making this much more modular and viable for other RPC mechanisms, and for being a general Nova component broken out for other RPC mechanisms to utilize. So this is essentially a back end, a front end for searching for hosts through a directory service. This can be implemented by a hash table. That's the way that it's currently implemented, and this actually works surprisingly well because we have only a very limited number of hosts that we really are mapping from these bare topics. The two topics that really seem to matter are scheduler and network. And in the case of network, if you're using the multi-host networking in Nova, it's actually not used at all. It's only used in certain networking models. And in the case of the scheduler, it's kind of it is a requirement, but you generally will have a fixed or semi-fixed number of schedulers that you're going to define in an environment. So with something like Chef, you can kind of update this and push this out in a fairly reasonable way. So a hash table is surprisingly effective. But you can implement this through a name service such as DNS, directory service, and really what's interesting is you can actually like micro-schedule this. You can use something like Zookeeper. You can micro-schedule and say, well, we want our scheduler to determine what compute host brings them instances, but we want to like actually schedule which scheduler we have scheduling our hosts. I think that's overcomplicated, and I'm not sure at this point if people want to do that. I think at the moment the community seems to be rallied around doing a hash table, but this is pluggable. So if you want to do if someone wanted to implement an esoteric directory service lookup, that's available to them to do without breaking everybody else and how they might want to do it. So this is the fan-out cast, and this essentially just shows how we integrate the matchmaker into doing a cast call, similar to the other examples that we showed earlier. And this is doing a cast to a general topic such as compute. in reality, this would probably be the topic would probably be scheduler again, since so we weren't supposed to this advanced prematurely to a different the next slide. So a brainstorm topic that came from this is that with the ZeroMQ driver, there's a cap theorem which says there's in a data store access model you have consistency, availability, and partitions and partition tolerance, and that in any distributed data store you can essentially a NoSQL database, for instance, you can have any two of these three. You can kind of accomplish the third one, maybe in certain ways, but the theorem is essentially that you can't really get all of the above. It's kind of pick any two, and you can see that there's a number of products that fit within each of these overlapping segments here. And with the ZeroMQ driver in Nova RPC, we've actually gotten to a point now where one could argue that we're actually overlapping with partitions and availability. So we have a similar functionality to DynamoDB, CouchDB, Cassandra, SimpleDB, Tokyo Cabinet, React, and so forth. So there's a lot of room for us to leverage this besides simple RPC mechanisms, and actually not to say they replace the database, but to there's certainly a lot of room within Nova to better utilize the RPC mechanisms and to use the data that's available within the system more effectively through RPC. And we can certainly show here that there are actual database products that follow this pattern, and we actually don't need to use those database products because we have this sort of as a built-in side effect of what's already available within OpenStack. So I do thank you very much for attending or reading this online or listening online, and there is a Essex plugin download on GitHub. It's APL sourced. This is the this will default to the Essex plugin, and there are alternative branches on that repository for Folsom, at least until we are merged upstream. And the slide deck is also available at the following URL. Again, thank you very much, and goodbye.